The next question is going to look at several array sorting algorithms. There are many array sorting algorithms, which will take an unsorted array and put it in sort order. With array algorithms, I want you to know how the swap algorithm works. I want you to understand the complexity of array search algorithms, the sequential search versus the binary search, and when do you have to use the sequential search, and what has to be the status of an array for a binary search. So here we're going to look at the selection sort algorithm. This is from the textbook, and I will also have a copy of this source code that you see available with the question. In addition, I have a video for you to watch to help you understand how this algorithm works. Let's say we have this 5-element array. Notice it's not sorted, and you're going to use the algorithm here to decide what the status of the array is going to be as it steps through your sort algorithm. The selection sort uses a nested loop, and the outer loop is going to loop from element 0 to the length -1. You will be pointing at one of the elements and then going into the inner loop and trying to determine if there's a smaller element. So the inner loop will assign a smallest value, whatever I is in the outer loop, and then it's going to start at I plus 1 and go through the entire array. Notice it starts at I plus 1 and it goes the entire length of the array compared to the inner loop. What it's doing is trying to see if there's something smaller than I. So if this is I, the inner loop is going to make that J, and if is that less than that? Is 1 less than 5? Yes. It's going to assign not this one, but the fact that this is index 1 to smallest. It'll go to the next. Is that less than 1? No. Is that? So it goes through the loop with the smallest being I, and it's done with that loop. After it's done with the inner loop, it comes down and calls the swap algorithm. The swap algorithm is an algorithm that I want you to be able to know. We'll go through that in a minute. So the first time through the array prior to the first pass, here's our array. And then we're going to swap 1 and 0. I is going to be 0 and J is going to be 1, and that gets swapped. Let's take a look at that swap algorithm. There may be a number of different algorithms in which you would want to call a swap method. And sorting arrays is definitely one of the major algorithms that you would use this for. But the author starts with an example where we want to reverse an array. So we are swapping the 3 and the 78. Well, or we're swapping what's in index 0 with what's in index 5. The author then mentions this is not going to work. If I assign to x the 78, and then I assign to y whatever's in x, well, we just replaced x with 78. You will end up with two elements with the same value. So when you write a swap algorithm, you will need to declare a variable of the same data type as the data type of the array. This semester we've been making the array be an integer, but actually it could be any data type. It could actually be an array of objects. Unfortunately, in an array, the swap method is not going to work if you make the parameter variables just integers representing the data. If you make it integers representing the index values, it will work. But if it's just representing the value of the elements, it won't work. Primitive data is passed by value, not by reference. This one will work. In this one, the array is being passed, and you will need to pass the array if you declared it inside a method. If you declared an array inside a method, it's local to that method, and to call the swap method, you will want to send that array as a parameter. Remember, when you're sending an array or any object as a parameter, it's just sending a pointer to what address in RAM. It's not picking up all the data and sending all the data. Just here's where the array is. It's starting right here in RAM. Then we're going to send I and j, not the values inside the element, but the index values. So we're going to use those index values to do the swap. Take listed I and assign it to temp. Take listed j and assign it to listed I, and then take temp and assign it to j. So what I remember is we're going to declare temp in here as a local variable, but temp starts it and temp ends it, kind of envelops it. If you use I here on the right, you're going to use I here on the left. Well, since I've used I here on the left, my only option is j here on the right and j here on the left. I think you can memorize that, and I hope this swap algorithm makes sense. Do read through this. This is in chapter 7.2. So we're coming back to our selection sort, and each pass will have it sorted one more, because what does each pass do? It finds the next lowest value that's being stored in I. So here we have 1, 2, 3. Now we'll find the next lowest, which is 5. By 4 passes through the outer array, we have a sorted array. So here's some questions you may be asked. What is the status of the array after the second pass? So you should be able to tell me 1, 2, 3, 7, 5 in that order. You will need to understand the algorithm well enough to know what will be sorted and what will not be. Another question I may ask is how many passes will it take? And notice with the selection sort, if it's a 5-element array, it's going to take 4 passes. If it's an n-element array, it will take n minus 1 passes. Next, we'll look at the insertion sort algorithm for sorting an array. This was not covered in the textbook. However, it was covered in the additional reading, and I have a hyperlink to that so that you can take a look at it. Here is an example of the source code. And finally, there's a link to a YouTube video for you to understand how to step through this algorithm. Here's our Canvas page on the insertion sort. Notice this is a nested loop, written in pseudocode for you. Generally, how this works is that we're going to be looping from I equals 1 to n, and we're going to assign this value 9 to the variable key. We're going to go 1 to the left of the key because to the left of the key should already be sorted. We're going to consider that like a subarray, and this is already sorted. If it's a 1-element array, it's always sorted. We will loop and decide if we need to swap or if this is already sorted as it is. In this case, we do need to swap, and by the time that outer loop is done, 1 pass, we will have a 2-element array sorted. I will become 2, making the key 30, and we'll do the same thing. It's going to compare actually the 30 to the one prior. That's the j equals I minus 1. Since 30 is greater than that, there's nothing that's going to happen, and we are now sorted to 3 elements. Loops back up to the outer loop, and I will become 3, and 10 will be assigned to key, and it's going to check in the inner loop to decide where it needs to then place this value 10. So that is the insertion sort. You're kind of building a sorted array 1 element at a time and making the decision where to swap. Let's apply the insertion sort to this array. So initially, key is 1. J will be equal to I minus j is here at 0. And we're going to see in the inner loop, do we need to swap? And so after the first pass, the status of the array or the state of the array will be 15372. Okay, next pass, now the key will be 3, and then j is going to be 1 less than that. Do we need to swap that? And by the time we get through the inner loop, the decision will be made that 3 belongs here. And we're in the outer loop again. The key will become 7. The inner loop is going to make the decision where that 7 needs to be swapped, and it doesn't need to be. So we're back to the outer loop one more time. and the key will become 2, and the decision needs to be made where in the inner loop where that will be swapped. So after this last element has been selected and decided in the inner loop where to swap, then the outer loop is done and we have a sorted array. If I asked you the status after the first pass, you would write this down for the status. How many passes will there be? Just like the selection sort, there will be n-1 passes to complete the sort. You will also be given a snippet of code and asked to determine the complexity of that algorithm, the big O notation. What you really want to look for are whether or not you have loops, nested loops, triple nested loops, etc. That's the key to figuring out the big O notation. Here's the Canvas page on sorting algorithms again. And if you recall, these sorting algorithms had nested loops. They have a for loop inside of a for loop. That's the selection sort. Here's the insertion sort, a while loop inside of a for loop. That gives it a big O notation of O(n) squared. So big O notation is known as the complexity of the algorithm, and it determines how fast or how slow this algorithm will run. In general, sorts can run pretty slow, especially as an array gets larger. Do review the Canvas page in week 7 on program complexity. And there are some examples of algorithms. Doesn't matter what this statement is as long as it's not a loop. So this would have a complexity of 3 because it's 3 statements. Here is a loop that's not nested. There's a complexity of n. A loop that's not nested with 3 statements, complexity of 3n. So the complexity of this would be 4n plus 3. So step through to determine the complexity of this. So the complexity here is 4n plus 3. The big O notation in general will just be n. Because the 3, as n grows large, the 3 is insignificant, adding the 3 to that. As the n grows large, multiplying it by 4 also is considered insignificant. But what is significant is when n is squared or when n is cubed. If we take a look at this algorithm, this is 1. That's a statement, that's 1. And here is a for loop with only 1 statement, so that is 1n. And then we're returning a value, so that is 1. So if you look at this, this is n plus 2. N plus 2 statements outside of the for loop. In big O notation, as n gets large, that constant 2 is insignificant. So the answer for this in big O notation is O parenthesis n.